So first of all, let's talk about binomial distribution. It's a discrete distribution and we're going to discuss that in a few minutes. So here is a typical binomial distribution problem. The formula we're going to use are D binom and P binom. D will give you exact number like exactly 8 and P binom will give you cumulative like 8 or less. This is a very standard way of naming R functions in probability. We use letters like D, P, Q, R, etc. Let's now go to R. Probability of success is 25%, number of trials 40, and number of success we are looking for is 8. So first of all, let's run these ones. Run. So we have now our environment has the values. Now I'm going to slide this one down to get the other function that we have. There we are. So D binom will give you exact value at a point. P and P are cumulative. When lower tail is true, we start from the lower side, that becomes 0. That will be 0 through 8. If lower tail is false, we're looking at the other side of it. So let's now run this one first. And 0.1178, which means if we have 40 parts, probability of defective is 25%. There is about 11.78% probability that we'll get 8 parts defective. How about 8 or less? That will be right here. Run it and there we are. 0.2998. And this one 0.7001677. As you can see, these add up to 1. 29.9, 70, they add up to 1. How about between 7 to 13? And we actually have 2 ways of doing it, more like 3 ways of doing it. I can find using this function probability at 7, then 8, then 9, then 10, so on, and add them up. Or I can use, suppose, this function. I can find probability from 13 to 0 and then 6 to 0 and take the difference. And that will be 13 through 7. But I'm going to do slightly differently just for the fun of it. Because the vector part of R is very powerful. Let's define a vector Y that will be between 7 through 13. We're creating a sequence 7 through 13. So if I suppose run it, I get 7 to 13. If I suppose show Y here, it will give me 7, 8, 9, 10, 11 to 13. Now we're going to use this one. So D, B, I, N, O, M, Y, N, and P. This will give me the probabilities of 7, 8, 9, 10, 11, all the way to 13. And there they are. Well, I wanted the total of it, right? I can simply put SUM, sum, here. And when I run it, I get my answer. 0.8005437. So this is what we have done. To find the probability between 7 to 13, I could have either used this one that will be, let's just do it anyway. So we do P, B, I, N, O, M, 13, and P minus P, B, I, N, O, M, 7 and P. Actually, I need to use 6. I didn't put the lower tail here because by default, that's the case situation. When I run it here, I get 0.8005437. Exactly same thing here, same thing there. So we can do whichever we want to do it. Now we're going to do is plot. So let's suppose now we're going to do here. I define my vector 0 through 40. Earlier I had a vector y which was 7 through 13. Now I'm going to do y through 40 because we have 40 trials. What you'll see here is in environment part here, it will change. So run again, and now y becomes this one. So in environment part window, you can see what values you have right now. We have n40, peak 0.25, x8, and this one there. Yeah. Then I'm going to use a vector b1 to hold all the probabilities from 0 through 40. And let's do that. Run, and we got the vector. So b1 right now has the probabilities right there, 1, 2, 3, 4, 5, etc., all the way to 40. Then we're going to plot first height of b1. Run, and there is the height here, right there. What if suppose if I do the line with L, type equal to L, type equal to H. When I do this, we get a graph like this one. So what we are seeing really is that after some time here, it's pretty much all zeros. It's all zeros here. So I'm going to change this to 1 through maybe 22 or something, just to see. Then the graph will look a bit better. So let's change this one to 1 through, let's say, 22. And now if I have to run it again, and you'll see this will change. Run, and it changed now to 22 there. And now we're going to find the probabilities. Run again, and height. Run again, and now we have a bit better view of the probabilities. And if I do line, run again, and there we are. So why cannot we use the normal distribution to solve binomial distribution problems? And that's what we are going to do now. So as we saw earlier, binomial distribution in shape looks like normal distribution. So why can't we use normal distribution to solve the problems? Well, the catch is that they don't match. Binomial distribution is discrete and normal is continuous. That means that this is binomial distribution. Things happen only at 10, 11, 12, 13, etc. That's normal distribution. Things happen everywhere. So how do we manage this thing? Well, this is how it looks like. For discrete distributions, only lines matter. For continuous, the whole area matters. So if I only find probability at 10 and 11, what happens in between, like 10.5, 10.3, 10.7, right? So that's a problem. So our solution is bit creative this way. So for instance, number of heads is 9. Well, that's 9 right here. What we are going to do is we are going to start 9 here and go till here. So 9 will be actually not a line. 9 is an area 9, like area 52. Similarly, 8 will be starts here and ends here. 7.5 to 8.5 is 8. So now, for instance, if we go between 7 to 13 heads, what do we do? Well, that's like area 7 to area 13. Not line, but area. My 7 starts here. 7 is from there to there. And my 13 is from there to there. So when I say 7 to 13, I'm going to start my 7 right here and go all the way to 13 will be right here. So that basically means 6.5 to 13.5. So what we're doing now is converting our lines into areas, and then we're going to use a formula for mean, NP, for normal distribution also, just like binomial distribution. Standard deviation, same as binomial distribution. Then we're going to use normal distribution functions and find the areas like these ones. and then we'll be done. So that's our strategy when we go to R. Now we're going to find the mean and standard deviation of binomial distribution, which will be the same as normal distribution. We'll be using that one too. So here is the mean and here's the standard deviation, the formulas that we have. And this is the print that we're going to do. Sigma will be printed only up to 3 decimal places as opposed to 7, 8, 9, whatever it prints it. So let's run it now, this one. And we got mean 10, sigma 2.739. Again, mean 10, sigma 2.7386, whatever. We rounded it here. Okay. Now we're going to find the probability of 8 success using binomial distribution. We already did it before, so we're just going to do it again. Let's push it slightly down this way. Okay, so 8 success is 0.117871. 0.117871. Now we're going to do normal distribution success. Well, for that one, remember what we discussed, that for 8 success, we're going to do 7.5 to 8.5. It's not linear 8 anymore. It's area 8. Area starts at 7.5, ends at 8.5. So we're going to use N8, find area from 8.5 to minus infinity, minus 7.5 to minus infinity. The remaining will be 7.5 to 8.5. And we're going to print again here N8. So we run it again. And what we get is 0.11128, 0.1178. We can see here, right here. So our B8 is 0.1178 and N8 is 0.1112. So you can see it's 11.78, 11.12. Pretty close to each other, these two. So that's why we call approximation. So let's now do one more, which is we're going to find between 7 through 13. We did this before. So for binomial, it will be, we define the vector 7 through 13, and we're going to sum it up like we did earlier, and we'll get the value here. For normal distribution, we are going to do 13.5 minus 6.5. Once again, 7 is area 7 from 6.5 to 7.5. 13 is area 13 from 12.5 to 13.5. So we're going to take difference between this one minus that one. And let's see how these things look now. Okay, so we have binomial is 0.8005 and normal is 0.7987. So you really see 80.05%, 79.87%. It's even much less difference between the two. So what we're saying is that normal distribution really can work for binomial distribution. The only requirement is that n times p and n times 1 minus p have to be at least 5 or more. 5 or more. And this is the end of our video. We are done now. Wait for the other videos to come, and a bunch of them will be coming.